This is quite weird. Okay. Can you hear me at home?
Yes, I can hear you.
Okay, that's weird because they're different settings than last time. All right. Well, let's see. All right. And let's see. Okay, well, let's get going. So a couple of announcements. I think that we finally have everybody done with the exam. So I'll be grading the essays now that I can grade all the essays at once. And it's taking a little longer than usual to get the results back to you because of the need to schedule people who can't schedule, you know, in the time that we usually would have this exam, but we'll get it done pretty quick. Second thing is for those of you in the lab, I have decided, in keeping with trying to make things not suck and trying to make them as easy as possible, when you're done with that demography lab, not demography, but when you're done with the dispersion lab, just send it to me by email. Make sure it's a format that I can actually view on a PC, meaning that it should be either a PDF or a Word document, one or the other. If you've got a Mac, be aware that you need to actually save it in that format. You need to go to Save As and save it like that. So if you're in the lab from now on, we're just gonna, my original idea was that we would all be together in a big happy family, and no, that's not happening. So let's just submit the lab reports electronically, and we'll just deal with it, okay? So I would like all of those dispersion lab reports by the end of the week. And if anybody has a problem with the dispersion lab, you need to let me know. Yes, we have a question. And if you've turned yours in already, I've got you. Don't worry about it. We'll just, the next lab that we're going to be doing, you can just feel free to send that electronically. Okay. All right, so we're going to continue our slog through the math of life tables. And this is where we left off. We were talking about how you can depict survivorship graphically and sort of get a real quick understanding of what a population is doing and how it's doing it. So on the top left, we have a type 1-ish life table or survivorship curve for the plant phlox. And then on the bottom left, we have again, type 1-ish curve for rotifers. And they're never going to look exactly like that cartoon, where it was kind of a perfect curve. There's always going to be some mortality early. Even humans have that. So it's not going to look perfect, but you can tell that most of the mortality in these two species happens late in life. In the middle column, you have sparrows and robins, and this is really typical for songbirds. They have a relatively constant rate of mortality over the course of their lives. And so when you plot it on a log axis, which is why we use the log axis, notice that it winds up being more or less a straight line. The mud turtle at the bottom is a little bit trickier because it looks like it has a lot of mortality early, and it does. So what you say then is, well, it's mostly type 2 from the age of about 2 years on to the end of their lives. So as I said, they're not any of them going to be perfect. They're going to mostly be type 1, type 2, or type 3. And then on the right, you have Cleome, which produces 1 million seeds, of which only 20 or 30 survive. So that's clearly a type 3 curve. Yes, question. Okay, so the question is, do we know why these species have these mortality patterns? And the question was directed at the songbirds, but it's fair to ask it for any of these species. Well, it's just a factor of what their life history traits are, number one, and number two, what the environment is that they're living in. So their biotic interactions with other species help determine what these patterns are. But mostly this is an outcome of natural selection, selecting life history traits. So on the left-hand column for phlox and rotifers, although these are small organisms, they are selected to compete. And so we would consider these to be maybe not K-selected species the way we are, but they are, relatively speaking, K-selected. They have traits that help them live a long time and compete. On the other hand, the other extreme, Cleome, is clearly an R-selected species. They are selected to try to withstand catastrophes and have at least some of their offspring survive. That's mostly what's driving this. So right now, if we don't have any further questions about the survivorship part of the table, let's complete it. And then let's move on to see what we can do with this. So we'll fill in then if I can get it to respond. Come on. How's this happening? Oh, well, I may have to do that. Okay, we'll do that. All right, so Now we're going to add in the rest of the columns in the life table and do the reproduction part. And there are 3 columns that we're going to work with. First is the age-specific fecundity, or B sub x, B for birth. So B sub 0 is the birth rate of newborns. B sub 12 is the birth rate of 12-year-olds. And of course, you got to remember that I'm using years because that comes naturally to us. It could be days, it could be weeks, it could be months. So this is something that we typically measure in a population. We may need to calculate it if there's a missing value, but this is something we typically get from the population. So the number of individuals, N sub x, and the fecundity, B sub x, are things that we usually measure. And we base our rates in the life tables off of these measured values. The second thing is the age-specific reproductive rate, which is LX times BX. Now, this is really important. This is a key thing for understanding population growth, stability, or decline. Because, yeah, you can have the possibility that, say, a salmon might have 10,000 babies at the age of 8. But does that mean a newborn salmon can expect to have 10,000 babies? No, it does not, because you have to take into account the probability that it will survive to do that. So the probability of surviving to do that is LX. So LX-BX is actually way more informative about what an individual can expect to do at a particular age. It includes the probability of surviving to age X. So when you're talking about what a newborn can expect to do in terms of reproduction, you never use BX. You use LX-BX because it accounts for the probability that that newborn will survive. Okay, the final thing in the reproductive part of the life table is reproductive value. And this is crucial for managing populations. If we want to say, well, you can catch fish that are this big, but not this big, you have to put them back. Usually it's because we're estimating the reproductive value of particular individuals and saying, okay, if it's over a certain size, that's one of the key reproducers. And if we harvest them, we will kill off this fish stock. So we can't do that. So reproductive value then is the number of offspring an individual of age X can expect to produce through the remainder of its life after reaching age X. So these 3 things have some things in common with the other part of the life table. First off, BX and LX-BX are pretty easy to calculate. So on an exam, they're worth less than VX, the reproductive value. That takes a little more calculation. And the calculation is similar, but not identical to life expectancy, E sub X. Okay, there's a key difference where you start. And so you need to pay close attention because there's a slight difference in where you start adding up the numbers in the LX-BX column compared to where you start adding up the numbers in the LX column to get life expectancy. So let's work through this with an example. So here, I'm just giving you some fecundity numbers, okay? And we have a critical assumption here. It makes a difference. Organisms reproduce at the beginning of an age interval. So they turn 6 years old, boom, they reproduce. And after that, they may survive to the age of 7. But you see, it makes a difference in what you assume about this. Because if a 6-year-old reproduces at the end of that interval, then it has to survive to almost the age of 7 before it reproduces. And so there will be fewer 6-year-olds reproducing at the end of the interval than there will be at the beginning. So it's simplest to assume that they reproduce as soon as they reach that age. Now, this is an assumption for our ecology class. In real life, in real populations, an ecologist has to know. An ecologist has to figure it out. Do they reproduce at the beginning of that interval? Do they reproduce at the end of the interval? Or do they reproduce kind of all through the interval, kind of at random? It makes a big difference when we do these calculations. But for our class, they reach that age and they reproduce, bang, immediately, because that's easiest for us. So here's our fecundity numbers. What you can see then is that newborns don't reproduce. 1-year-olds don't reproduce. That means there's a juvenile phase. And then they start reproducing at age 2. A 2-year-old can expect to produce 1 offspring if it lives to the age of 2. And after that, you have a peak in reproduction at age 3, and then it falls off. This is senescence, right? Organisms become less able to function as they get older. So this is what we're going to base this on. Usually, you get most of these BX numbers. Sometimes you may have to calculate one if it's missing, but these are generally in real ecology problems. They're generally obtained by observing the population. All right, so how do we proceed? Well, here's the LX-BX column, and it's simply LX times BX. So for the first couple, 0 times anything is 0. So LX-BX is 0 for ages 0 and 1. For ages 2 and up, though, you're multiplying numbers by other numbers. So for LX-BX for age 2, that is L2B2, we have 0.4 times 1, or 0.4. For L3B3, we have B3 of 3 and an L3 of 0.3, so it's 0.3 times 3, or 0.9. All right, now this is a really crucial piece of information for us, this LX-BX column. It helps us understand what's happening with the population. Is this growing, declining, or stable? Now, reproductive value is a different matter. You have to think about how many offspring an individual could produce if it lived to be that age. So here's how we figure that out. And this is where the assumption that they reproduce at the beginning of the interval is really important, because it affects which terms we add in. So Vx is going to be the sum of the LX-BX column all the way from the age of X, because remember, if they survive to the age of 3, they reproduce at the rate that they would at age 3. They don't have to survive through the age of 3 and reproduce at the age, at the end of the interval. They reproduce right at the beginning. So we count the current age. L3B3 gets added in to the reproductive value of a 3-year-old. Okay, and that's the difference between life expectancy and reproductive value. If we were calculating life expectancy, we'd say, well, these 3-year-olds have reached the age of 3, so what we need to do is to add up L4, L5, L6, etc., and divide by L3. But for the reproduction part, L3B3 counts, because when they reach the age of 3, they then will produce those offspring. So let's work through the Vx column. So first off, what's V0? What's the reproductive value of a newborn? Well, it would be L0B0 plus L1B1 plus L2B2, etc., divided by L0. So it's the whole column. And it's 0.4 plus 0.9 is 1.3, plus 0.4, which is 1.7, plus 0.1, which is 1.8, divided by 1. And so it's 1.8. Now, what's the reproductive value of a 1-year-old? Did you have a question? Or you're just working through it? Yeah, you just, okay, using your fingers to work. Okay, this is good. That's what you need to do. What's the reproductive value of a 1-year-old? Well, notice that half of the individuals have already died. So logically, the reproductive value of a 1-year-old ought to be roughly twice what the reproductive value of a newborn is. Because if half the newborns die, then whoever is left has to do all the reproducing. So let's add it all up. Well, it's 0 plus 0.4 plus 0.9 plus 0.4 plus 0.1. That hasn't changed. It's still 1.8. But now we are dividing by L1. And L1 is now 0.5. So it's 1.8 divided by 0.5, which is 3.6. Okay, and I have this in here quite deliberately to show you how this has to work. If some of these individuals die, the ones that remain have to do all the reproduction. Okay, so how about a V2 for 2-year-olds? Now, this is the first age that actually starts reproducing, right? So you count L2, B2 here because they reach the age of 2, they reproduce. So L2, B2 counts. Not like life expectancy where L2 would not count. This counts. So it's 1.8 divided by now 0.4, which is L2. And so that winds up being 4.58. Now notice the reproductive value increases, and that's because of this early mortality. Everybody who starts reproducing has to reproduce at a relatively high rate to make up for the fact that, hey, a bunch of individuals have already died. So you can expect the reproductive value of any population to kind of maximize itself at about the age of first reproduction. The exact reproductive value, the exact highest reproductive value will depend a bit on the schedule of births and deaths, but reproductive value increases from birth to the age of first reproduction for every species. So we can do this for the remaining values, and what you see is for V3, you'd add up 0.9 plus 0.4 plus 0.1, that's 1.4. 1.4 divided by 0.3 is 4.66. For V4, it's 0.4 plus 0.1, which is 0.5, that's easy, divided by 0.2. And that's 2.5. Okay. So I've thrown a lot of math at you about how to fill in these tables, but guess what? I've posted 4 life table practice problems on the problems page on the Moodle site. I've also posted the answers. At least I think I got that 4th one posted. Maybe I only did 3, but I'll get them all up this afternoon. Please try to work through it before you look at the answers. The answers give you very detailed instructions about how to find missing values. Okay, and that will be the kind of problem that you will get on life tables on the exam. Won't be the only one, because this appears again and again over the next few lectures. But this will be a major component of the next exam, how you actually calculate life table values. All right, so now we have our complete life table. We've left out the life expectancy to save space, make sure these numbers are big enough. Now, what is the net reproductive rate? We have to remember what the definition of the net reproductive rate is. It is the number of offspring that a newborn can expect to produce over their lifetimes. And if you think about it for a minute, you'll see that it's just the sum of the LX BX column. In this case, for this population, R0 equals 1.8. Now, this is really important. If an individual newborn can expect to leave more than one offspring over the course of its life, that means the population will grow. If a newborn exactly replaces itself and has one offspring, exactly one, that means the population will be stable. And if a newborn has fewer than one offspring over the course of its lifetime, obviously, this population would decrease. So R sub 0 is a crucial measure of population growth. It is our first one. We will derive all of the other measures of population growth basically from R sub 0. Now, something that you may have run into in the news over the last 17 months now, or is it 18? It's now 18 months, is the term R sub 0. R sub 0 is also the metric that we use to determine if an infectious disease is spreading or declining. We calculate it exactly the same way. Except for infectious diseases, what we're asking is for each infection, how many more people can be infected before the host either recovers or dies. Okay, and for the coronavirus, sometimes it's been 1.8, sometimes it's been 2, sometimes it's been 5. If you have an infectious disease that has an R sub 0 over about 1.5, that is a rapidly spreading epidemic. Okay, we will come back and talk more specifically about this when we talk about parasites. But this is probably not the first time you've heard of the term R sub 0, whether you know it or not, and it's not the last. Okay, now we've been working with a dynamic life table with a cohort that was followed from birth to death. So we've accounted for every single individual. One of the challenges of working with life tables is that sometimes you get a static life table and you get a snapshot in time. And here's an example of the challenges you have trying to work with static life tables. Okay, so what we have here is on the N column, notice that we had a real excess of births a year ago. And so this is just a random thing that happens in populations. Sometimes you have good years, sometimes you have bad years. But this is a problem for us in calculating things. You would not be able to calculate L sub 1 from this information because there's actually more 1-year-olds than newborns. Well, that's a common problem with static life tables. It's a common problem in ecology. And when I give you a static life table, I will not simply give you one column of numbers. I'll give you two. So you have N at time 0, you'll have N at time 1. That is the way that you can work out all these rates in a static life table. You have to have more information. So for a static table, you can't just assume that you can calculate everything directly from the numbers in the N column. You have to have two sets of numbers. You have to have N sub 0, and you have to follow those individuals at least for one additional time period. So when you get a static table to work on in the problems, you'll always see two columns of numbers. So you'll be able to tell that if you had X number of newborns at time 0, they'll be the 1-year-olds in the second column. And so you will be able to calculate that. You can't calculate it if you have just one column of numbers. So here's an example of how that would work. So even though you cannot calculate a survivorship based on 100 newborns and 120 one-year-olds, if you have two sets of numbers, if you followed them for at least 1 year, then you can figure it out. So here you see that you had 100 newborns at time 0 and 50 one-year-olds at time 1. All right, well, the 51-year-olds at time 1 were the newborns at time 0. So there you can use that information to calculate LX and SX. So whenever you get a static table, you have to do extra work to do the calculations. But if I'm going to give you a problem like this, I'm going to give you what you need to answer the question. So you can't directly calculate it from the change in N at time 0 because there are more one-year-olds than newborns. That makes no sense. So you need the extra information, and you will always have it. So we have two samples of numbers for static life tables always. And that's one way you can tell that you're working with a static table in a problem that I might give you on the exam. If you're just looking at an n column and you've only got one n column and you see the numbers don't continuously go down, they go up and then down, well, you're working with a static table. So you got to ask yourself, well, what's he getting at with this? What's this all about? So whenever you have a static table, you will get the information you need. Now, I need to emphasize that this is really crucial. This is one of the most important things in all of ecology, working with life tables, because they furnish us with the information to calculate population growth. So it's kind of a big deal. I do want you to do your best here. I want you to take these calculations seriously. And you need to treat it, as I said last time, like either a crossword puzzle or a Sudoku puzzle. It's a puzzle. If you like puzzles, then life tables should be something you can adapt to without too much trouble. If you despise puzzles, then you're going to have to do a little more work. But that's what these things are. It's just a number game. And if you treat it that way, maybe it won't be so horrible. Okay, so that's our walk through basic life tables. We're going to finish this up with our next presentation on what you can do with life tables. And you'll see, I think, immediately how important it is for us to understand this, because it will give us the information that we need to do population growth. And let me close that out. Okay. So while I'm getting the next one, that is this. Okay. Does anybody have any questions so far? Where's our, well, doggone it. Oh, there, it's up there. All right, so we've got these life tables. What can we do with them? Well, we can do a couple of things. They have some assumptions, though, and we'll show you what those assumptions are. First, we can predict what a population will look like in the future. Knowing the vital rates, that is SX, MX, BX, we can predict what a population will look like in the future. And knowing what those rates are, as long as they don't change, we can project a year into the future. We can project 10 years into the future, 100 years into the future. But the assumption then is that the rates don't change. What we will see is that if the rates don't change, and we're going to be mostly working with the S sub X column and the B sub X column. If those rates don't change, the population will converge to a stable age structure over time. So you'll always have the same proportion of newborns, the same proportion of 1-year-olds, 2-year-olds, 3-year-olds in the population forever. Of course, this is completely unrealistic because, of course, those rates do change. But this is what we need to understand how to work with life tables and apply them to population growth. When you get to a stable age structure, you can then calculate the geometric growth rate, which is the growth rate of the population, not over the course of an individual organism's lifetime, but the growth rate over a defined period of time. So just because white-tailed deer survive maybe 15 years and humans survive at least 70, if you know the R sub 0, that's great, but you can't compare them because they're living different numbers of years. If you can calculate this geometric growth rate, lambda, you can compare the populations over a standardized period of time. There's also something called stationary age structure, which is a special case that I'll show you what it is. And you'll see very quickly the importance of the SX and BX columns in figuring this out. So here, let's have a very simple population with very few columns, well, with very few rows to make it easy so we're not calculating 100 different numbers. And so what I've got here is a very simple population where we have 3 ages. We have newborns, age 0, we have 1-year-olds, and we have 2-year-olds, and then everybody dies. Simple, easy peasy. And here are the survival rates and the birth rates. So the survival rate for newborns is 0.75. So S0 is 0.75. S1 is 0.5 and S2 is 0, which is consistent with us making everybody die after the age of 2. And then here's the birth rate. Okay, newborns have a birth rate of 0, 1-year-olds have a birth rate of 1, and 2-year-olds have a birth rate of 2. And here's some starting numbers. So if we have 20 newborns, 21-year-olds, and 10 2-year-olds in this population to start, how many will we have at the next time interval? And notice down here at the bottom, we've calculated the proportions. That's important because the proportions will eventually stabilize. The actual numbers here won't stabilize. They may grow, they may decline, but the proportions, we're arguing, are going to stabilize. Well, let's see how we do this. First off, let's look at the survival. So you have 20 newborns, and they survive to be 1-year-old at a rate of 0.75. That means you're going to have 15 1-year-olds in the next time period. 20 times 0.75 is 15. We do the same for the next generation of 2-year-olds, or the next year of 2-year-olds. And notice that we've got 21-year-olds. They survive at a rate of 0.5. That means you're going to have 10 2-year-olds at the next time step. How do we figure out the newborns in the next time step? Well, we simply ask who does the reproduction. Newborns, there are 20 of them, but they reproduce at a rate of 0. So that's 0. So they don't contribute to the newborns in the next time step. The 1-year-olds do, though. There are 20 of them, and each of them has 1 baby. So we know that there are at least 20 newborns in the next time step. The 2-year-olds reproduce even more. There are 10 of them. They have 2 babies each. So we get 20 newborns from the 1-year-olds, 20 newborns from the 2-year-olds. That means that we're going to have 40 newborns in the next time step. So we'll have 40 at age 0, 15 at age 1, and 10 at age 2. And now we can calculate the proportions. Now, notice that they change quite dramatically. In the first time step, time 0, there were 0.4 of the 40% of the population was newborns. But in the next time step, it's 60%. It's over 60%. So that's a big fluctuation. Well, let's see what's going to happen over time. Let's do the next time step. So once again, we apply the survival values to the number of individuals in age 0 and 1, and we get 30 one-year-olds and 7 two-year-olds. And notice that if we were doing this exactly, it would be 7.5. But I don't work with half animals or plants. I work with whole. So we're going to round. And that's going to cause us to have some fluctuations that, that will make our calculations not exact. But on the other hand, it's better to have whole organisms rather than half organisms. We have a question. I will give you instructions about whether to round and how to round if I'm giving you a question like this. All right, so in time step 2, you see that you have 30 one-year-olds and 7 two-year-olds, rounding error. And then how many newborns? Well, once again, the 40 newborns at time 1 don't reproduce, so that's 0. But the 15 one-year-olds do, and the 10 two-year-olds do. So now you have 35 newborns, 30 one-year-olds, and 7 two-year-olds. And you have, look, your population grew. It grew from 65 to 72. So at least for now, it's a growing population. What's interesting is if you look down here at the bottom, the proportions have changed really dramatically once again. The newborns went from 40% of the population to over 60%, now to just under 50%. And notice that the two-year-olds went from 20% to 15 to just under 10%. So this is exciting, it's dynamic. I'm hoping you're waiting with bated breath for the next time step. And what we're going to do is just fill it all in now that you've seen how we do it. So, all right, here's where we go. We started with 50 individuals. We wound up with 65 at time 1, 72 at time 2, 85 at time 3. So this population is growing, right? The numbers here are changing over time. So we started with 20, 20, and 10. By the time we get to 8 time intervals, we have 100, 64, and 28. So it's a growing population. What's interesting, though, is how the proportions change. Not the numbers, but the proportions. So the proportions are on the bottom. And look what happens to them. So we go with the newborns, starting with 0.4, then 0.61, then 0.48. And then look what happens. They start to stabilize. They're stabilizing around a value of 0.52 or 0.53. I only took this out 8 time steps. We'd have to go further to see it actually stabilize. But it stabilizes, and it will not change forever. As long as the BX and SX values are constant, you will reach a stable proportion of organisms in each of the age classes. You will have approximately 0.52 or 0.53 of the population being always in the newborn class. You'll have somewhere around a third of them being 1-year-olds, and you'll have somewhere around a sixth of them being 2-year-olds forever. And the key thing is, the assumption is that the vital rates don't change. As long as survival and birth rates do not change, you will converge over time to a stable age distribution. Okay, so this is fascinating, right? You're saying, yeah, he thinks it's fascinating. But it is actually fascinating because something else goes on. Let's look at the ratio of population sizes from one time to the next as we converge to that stable age distribution. So we start out with 65 divided by 50 here, and that's an increase of 30%. So the ratio is 1.3. If we divide 72 by 65, that's the difference between N2 and N1, you'll notice that the ratio is smaller, it's 1.1. But look what happens to the ratio. As we converge to a stable age distribution, that ratio also converges. It converges to something like 1.17 something, close to 1.18. The key takeaway here is that when you reach a stable age distribution, the ratio of population size for any two intervals will also become constant. You'll have a constant rate of population growth. That is what we call the geometric growth rate, lambda. It is the ratio of the numbers at time 2 divided by the numbers at time 1, or the numbers at time 20 divided by the numbers at time 19. It's the ratio of n at x plus 1 divided by n at x. And that ratio becomes constant when you have a stable age distribution. That means that you can project population growth indefinitely into the future if you have a population with a stable age distribution. Dwayne has a question. All right, so Dwayne's question is, if the vital rates are not changing, are we also assuming that things like resources are stable and not changing? And the answer is yes, that is the only way that you can get the stability in vital rates. Everybody has to have more or less the same access to resources in order to survive at the same rate and reproduce at the same rate. Okay, and remember, we're not talking about every individual is guaranteed to do these things. We're talking about the averages. So on average, individuals survive at a particular rate. You might be one of the lucky ones, might be one of the unlucky ones, but on average, these are your survival rates. On average, these are your birth rates. Now, this property of populations, the stable age distribution, and our ability to project a rate of population growth into the future has some really special features. So here's a slightly different population that illustrates that these populations can grow or decline or be stable. Here is a population that has a schedule of survival and reproduction that makes it neither grow nor decline. And look what happens to this population. So we're starting out at time 0 with 40 newborns, 10 1-year-olds, 5 2-year-olds, and 5 3-year-olds. Here's the schedule of survival in the SX column and the schedule of reproduction in the BX column. Now, I had to go through a lot of trouble to find this schedule because it's not easy to find something that will give you a population that shows this property. So this was trial and error over several years. But what you can see is you start with 60 individuals, and then at time 1, you wind up with 53, time 2 is 56, and then 54, 55, 54, 57, 56, 56. It's very clear that this population is neither growing nor declining. It's stable. The key thing that we're looking at, though, is does this population converge to a stable age distribution? The answer is absolutely yes. Look at the bottom. Here are the proportions in each age class. And yes, you start out with about 2/3 newborns, 1/6 1-year-olds, that's 0.17, and about 1/12 2-year-olds and 3-year-olds. So that's 40, 10, 5, and 5. But look what happens as you go through time. By the end of the 8th time interval, you've converged to a stable age distribution. And this time, I got the numbers much closer. the stable age distribution for this population is 0.54 newborns, 0.27 1-year-olds, 0.14-ish 2-year-olds, and 0.05-ish 3-year-olds. This is a stable age distribution for a population that is neither growing nor declining. Okay, and this is a really special case. This is called a stationary age distribution. A stationary age distribution applies to a stable population. A stable age structure applies to a population that is either growing or declining. Stationary means the population is stable. Now, another interesting thing about this is that the starting numbers are completely irrelevant. It doesn't matter what your starting numbers are. You could have 10,000 newborns, or you could have 0 newborns. As long as the SX and BX values don't change, the starting numbers are irrelevant. You will converge to a stable age distribution over time, or a stationary age distribution, as the case may be, if the population is not growing. The numbers are irrelevant. It's the rates that matter. So here's our sample population again, and we had 40, 10, 5, and 5. Now we have this really weird distribution: 25, 0, 5, and 20. So this column here is all messed up. Okay, and notice that the proportions down here are way different from the proportions that we had in the previous slide. But look, it doesn't matter. It's completely irrelevant what the starting numbers are, because the stable age distribution winds up being 54%, 27%, 13%, and 7%. It's the same age distribution. So as long as the SX and BX values are consistent, you will get a stable age distribution regardless of your starting numbers. Okay, that's where I want to end for today. We will show you tomorrow, Wednesday rather, where we take this. We will wind up taking this from the geometric growth rate, which is kind of a special case, to a much more general growth rate, the exponential growth rate, which we can use to model any population, regardless of its lifespan, regardless of its schedule of reproduction, and we'll be deep into population growth at the end of next time. All right. For those of you who might have questions, I'll hang around for a minute. But if not, I'll see you on Wednesday. If you're coming to lab on Wednesday, be sure that you check the weather. We had good weather this week. Might not have good weather next week or this coming week. All right. So I'm going to sign off. Unless you have a question, make sure that you have typed something in the chat box if you're joining from home. And Luai, I see your account. Yes. Okay. Gotcha. Yeah. If you're using someone else's account, make sure that I type your name so that I know it's you. I have posted them. I posted them this morning.
Okay. I left the house.
Probably so. Oh, did I not get around to doing that? I may not have posted it yet, but I certainly will. It's a lot. It's a lot. Yeah. No, I'll post everything. Okay, guys at home, I'm going to end this and see y'all later.